Hey, a little while ago I stumbled upon an effect by somebody else on Twitter, and I thought it looked really cool, and I thought we could make it ourselves in ShaderToy. So I did, and I will explain exactly to you how to make it yourself. So if that interests you, then stick around. So let's start with a new ShaderToy, and let's make the size correct. And let's do some cleanup here. I'm going to go really quickly on the parts that I've already gone over in previous videos. If that is the case, then it will show up in a notification above. So then you can click on that to get a full explanation of how this works. Other than that, I'm just going to go through this pretty quickly in the beginning for anything I've already covered. So that's my UV coordinate, and then I'm going to go make a black screen. Black 3, 0, and there we go. So now what you looked at there was the inside of a torus, and what we're going to do for that is I'm going to make a ray marcher, and then we're going to put a torus in there, and then we're going to play with the material on it. So we're going to have to start with writing a ray marcher. Actually, we'll start by writing some camera code. So for that, I'm going to go vec RO for ray origin is, and I'm going to put my camera at 0 from left to right, and then at 3 above the ground plane, and at -3 like behind. And now I'm going to make a look at point, and for the look at, we're just going to make it that it looks at the origin. And then I'm going to make a zoom value, and I'm going to set that to 1 to start with. And now we have to make our ray direction. And for the ray direction, we have to do a few other things. So let me just write it out real quick. So I need a right vector. No, I'll start with a forward vector, which is the normalized look at minus the ray origin. And then I'm going to make my right vector, which is the normalized cross product between the world up vector, like that, 0, 1. Why did I write that twice? 0, 1, 0, and the forward vector. And then I'm going to get my camera up, which is the cross product of the forward vector and the right vector. And now that I have my 3 axes for the camera, I can calculate the center of the screen, of the virtual screen, which is the ray origin plus the forward vector times the zoom. And then I can find my intersection point where the camera ray intersects the virtual screen, which is the center of the screen plus uv.x times the right vector, and then uv.y times the up vector. And now that I have the intersection, I can get the ray direction, which is the normalized vector from the ray origin to the intersection point. And that should be like that. Now let's just visualize that real quick to see if I didn't make a mistake, which I probably did. Okay, so there's an O missing. Okay, this tells me it's correct. I get different view vectors across the screen. So let's get rid of that. So now we have to write a ray marcher. And for that, I'm going to go the distance to surface and the distance to origin. Those are 2 things that we need to keep track of. We also need to keep track of the point that we're currently at when we're ray marching. And now I'm going to make my loop. Int I equals 0, I smaller than, let's say, 100 steps, which is the maximum number of steps. And then inside of this loop, I'm going to update my marching position, which is the ray origin plus the ray direction times the distance from the origin. And now I'm going to get the distance to my surface. And my surface is going to be a torus. So I'm just going to write out the distance function for a torus here. Normally I would make a separate function here, get dist or something like that, and then up here I would make a complicated distance function, but because we're only doing a torus, I just do it inside of here. So distance function for a torus is the length dot p xz minus the large radius, and then I'm going to make that into a vector 2 with the p dot y, and I'm going to take the length of that thing, length, and that's going to go minus the small, like the thickness of the tube radius. So that's that, and now we have to check if we have hit something. So if my distance to surface is smaller than some small value, then we can break out of the loop. If that isn't the case, then we need to forward our distance to origin. We need to add the distance to the surface to step forward. Okay, so let's see if that worked. So I'm going to go over here and say if distance to surface is smaller than 0.001, then supposedly we hit something. So let's just say call plus equals 1. Okay, now we got something. Let's see here what I did wrong. Okay, so it's not 0.1 here for the large radius. It is 1. So now we're looking at a donut, at a torus from behind and from above. So now that we have that, we can get some UV coordinates going on this thing. And so for the UV coordinates, I'm going to use the polar coordinates. So if this is the middle of the torus here, then the one polar coordinate would be around the torus. So let's do that one first. So that is just the atan of p dot x and p dot z. And let's visualize that. So I just do plus x over here. And now you see that over here it's minus pi, and it goes all the way to 0 over here, and then from 0 it goes all the way to pi. So that's 1. So let's do the same thing for the y. So float y equals, and for the y it's a little bit more complicated, because for the y it would be like if you imagine the cross section here, which would be a circle, then it's first the distance to that circle, and then we have to take the height into account as well. So the distance to the circle is just this over here. So let me just copy that. The distance to the circle, and then I just do my p dot y over there. So let's try that as well. So now we have that, and whenever something comes out of an atan function, it's always from minus pi to pi, and that is very advantageous in this case, because if we can use that with trig functions like sine and cosine, because sine and cosine, their phase is exactly 2 pi long. So I can do something like this, and now if I multiply this by a whole number, then I will never get a seam. Okay, because it will fit perfectly into the phase of the sine. So let's put a bunch here. Let's say 10. So now I have that, and now I want to twist it. So what I'm going to do is I can add, if I add this x to here, then as it goes around the torus, it's slowly adding 2 pi. And that will make a twist. So let's see here. So now it's a bit subtle, but now you have a spiral that spirals in here. And we can multiply that by a larger number. Well, let me just first do that to tighten that twist. And as long as you keep these whole numbers, it will always fit perfectly. So that's awesome. All right, so now let's inflate this torus a little bit more. So the small radius right now is 0.5 over here. So I can make that larger. Let's make it 0.75 to have a larger torus with more interior volume. And now we want to go inside of the torus. So for that, first of all, I'm going to go to the ground plane. So now we're looking at it straight on. And now I'm going to go into it. So let's go right exactly in the middle. So the large radius is 1 over here. So if I set this to -1, now I'm exactly in the middle. And the reason why I don't see anything is because this gives me the distance to the outside surface of the torus, and in order to get it to the inside surface I have to invert it. So just put some brackets around it and put a minus, and now I'm inside of the torus. And now in order to see a little bit more, let's make the field of view wider. And in order to make the field of view wider, you get the virtual camera plane closer to the camera position. So now I can see more. So that's already starting to look pretty good. So now let's play with this a little bit. So let's call this bands over here. So I'm going to go float bands. And then I could do call plus equals bands to see. Well, it's the same thing. And now let's cut out these bands so that they go hard from black to white. So I'm going to go float b1 equals smooth step minus 0.2 comma 0.2 comma bands. And that just makes it that the transition is going to be harder. So b1. All right, that's already pretty cool. And now I want to make it that the white parts are kind of grooves that have edges and that are hollow in the middle. So for that I will just copy this to something called B2. And if you look at B2, it's the same like this. But now so this bands is a sine wave, right? So if I sink this sine wave into the ground, then the parts that are above this are above the x-axis are going to get smaller and smaller. So check the white part is going to be narrower now. And so now if I multiply those by each other, so let me just call this m here. So float m equals b1 times the inverse of b2. And let's look at that. Call plus equals m. So now we just have the edges. All right, so now I want to, inside of these grooves, I want some ripples. So for that, I'm going to copy bands here. I'm going to call this ripples. The ripples, and the ripples, I want them to be, rotated. So, and let's also look at this here. So now if we just look at ripples like that, in order to rotate something 90 degrees, you could just swap the x and the y and then make one of them negative. So I'll make the y negative. So let's see what that looks like. So that changes that. And also let me just change the winding here before I get too far. So I wanted 10 and 30 instead of 10 and 20. So that just makes the winding a little bit different. And now I'm going to make the frequency higher for the ripples because I want a bunch more ripples like that. And also I want these ripples, the ripple sine wave to go from 0 to 1 instead of minus 1 to 1. So I'm going to just multiply by 0.5 and plus 0.5 just to lift it above the x-axis. And now I want those ripples only to be visible inside of the groove. So let me actually get back over here to those grooves. And so now over here I could just add, let's say, the ripples like that, and then times, because I only want to show it inside of the groove, so I could just do times B2. And now it will only show inside like that. Okay. And maybe I want the blend to be different. So instead of just adding it, let me just use the max value here so that white is just 1 and not larger than 1, because sometimes it can kind of screw you up. So because sometimes you can't see, like you can't see negative values because everything is just black, and you can't see something bigger than 1 because everything is white. So it's a bit safer to do it like this. So that should not really change anything. You see it changed a tiny little bit on the edges there. Okay, so now I want these ripples to come in waves. So I will just copy this, and I will, well actually no, let me copy the bands part instead, like that, and I will call this waves. And actually, well, that was stupid because I still need to rotate it around, so I'm just going to still have to do that and this. So let's look at the waves by themselves. like that. I want the frequency of the waves to be a lot lower than this. So I have to, I can change these numbers, but they have to stay at the same ratio, and they have to stay whole numbers as well. So I can't just put any number here. But what I could do is, well, I guess I could just do this. So that should make a lower resolution wave, and then maybe, yeah, maybe I'll multiply this a little bit more. Yeah, something like that. And now let's see if we can blend this in somehow and still make it look good. So let me see here. So let me go back to the just adding M, the mask, so for everything but the wave. And now I can multiply it here by the wave. But again, I don't want to multiply it. If this wave can go negative, I don't want to multiply it by a negative number potentially. So I'm just going to do this out of safety. And waves. Okay, so that already looks pretty good, I think. So let's start moving this. Let's start animating this. So let me go over here all the way to the top and say float t equals I times 0.2, let's say. And then I can add, well, I could give the impression that the whole thing is rotating, not by rotating the camera or rotating the torus, but just rotating the texture. And for that, I could just, on this X here, I could just add T, and that will make it rotate. And that's a little bit fast for my taste, so let's make it a bit slower. Okay, something like that. And now we can also make those waves move as well. So over here, inside of here, I can just add T, and that's going to be way too slow, so I'm going to have to multiply it by a larger number, maybe even larger than this. Okay, there we go. All right, well, that's already starting to look pretty pretty disco-y. Let's see if I can just add a little bit more of the wave color. So if I just add wave here, and again, I have to max it with 0 because I don't want to add a negative number. Let's see what that does. Waves. Okay, that's obviously way too much, so I'm going to just add a tiny little bit of that. Yeah, maybe something like that, but only inside of the groove, so also times B2. Okay, well, it's kind of subtle, so maybe I'll just stick with this. Okay, so now this looks cool, but the inverse of this also looks cool. So if I do 1 minus M instead, then I get something like this. So why not have both of them? So I'm going to mix those together. So I'm going to mix the normal one and the inverted one, and I'm going to mix it based on the X here. So based on where inside of the torus we are. So and I could use a sine wave for that as well. So stick that into a sine wave and then get it into the 0, 1 range. And let's see what that looks like. Okay, so now we have we have the black version here and the white version there, and there's like a large fade in between. I don't want that much of a fade in between, so let me just stick it into a smooth step, and then I can just do minus 0.1, minus 0.3, come up 0.3, and then actually my sine wave can still be centered around 0. So let me see what that does. So yeah, that makes it that makes the transition a bit tighter. And then I don't want this transition to always be here, so I could maybe move that transition as well, like that. And then also maybe have it more often, that it happens more often. I'm not sure about this. Let me see. Yeah, we're not. I think it looks cool. All right, so now we can kind of screw with a bunch of parameters. So there is up here, there is the zoom. So if we zoom, let's say all the way out, then we get some super distorted screen, which looks pretty cool. So what we could do here is we could mix that. So we could do, well, maybe this is a bit too much. So 0.2 and then all the way zoomed in would be, let's say, 0.7. and then I take the sine of t times 0.5 plus 0.5 to get it in the 0, 1 range. Let's see what that looks like. So now it will zoom in and zoom out. Okay, so that's already pretty cool. And one other thing, and actually before I do that, so let me just set this to 1 here real quick. Not 1, let me set it to 0.5 so we can see what we can do. So right now we're just looking at the center of the torus. It's also cool when you look tangentially, when you look along the torus. So what I can do is I could look, if I look left, let's say vec2, so to the left is -1, and then the same height 0, and then the same depth, which is -1. And let's see what that looks like. So now I would imagine to look left. So now I'm looking left. I'm looking along the torus. So we can play with that as well. So what I could do is the same thing. I could do a mix of vec3 0, let's say, and this, and then I could use that same sine trick again. So times sine t times 0.5 plus 0.5, and then usually you want all these t's inside of the sines. You want them to go at slightly different speeds so that you get different combinations of effects over time. So let me see here. So now it starts looking left, and then when it looks all the way left, it will come back to the center. Okay, so let's do that together with the zoom. So you can see it starts getting pretty mind-bending right now. Okay, so that's pretty cool. And then let's also rotate the entire screen. So for that, I can just rotate the UV coordinates over here. So I can do, well, after my t, because I need my t for the rotation. So I can do UV times equals a 2D matrix of the cosine of t, and then the sine of t, actually minus the sine of t, and then the sine of t, and then the cosine of t. And that's just a default rotation matrix in 2D. So let's see what that looks like. So now we have some rotation going on. That's pretty cool. And then the last thing that I wanted to show is that, and for that I'm going to have to stop it when it looks to the middle. Okay, let's say over here. We can change the size of the tube. So we can go, let's see, over here. Go over here. So this is the size of the tube over here. So we can go over here and we can make that larger or smaller. Okay, so if I go over here and I go radius, and then I go over here, float radius equals, well, whatever, 0.5, that's what we had. So now we can play around with that. So 0.1 maybe all the way, and we can mix that so it's the same as what we did before. Oh, and actually, well, before I do that, so we started out with a radius of 0.5 like that, but we can go all the way to 1, which means that it will touch in the middle, and you can even go farther than 1, and then it will kind of turn into a different type of shape, which is kind of cool. So let's just do 0.3 and 1.5, and then with the sine of t times 0.5 plus 0.5, and then times some smaller value here so that it goes slowly. Let's see what that does. And let's press play on this. So we're going to look at this. And yeah, I think it works pretty good. So I hope you like this. If you like this, please like, comment, subscribe, click the bell icon. Maybe go to Patreon and see what perks you can have. Or what you could do is you could share this with your friends. That would be cool also. Anyways, I hope you like it, and I see you next time.